Hello and welcome everyone. My name is Gareth Leonard. I'm the Managing Director of Regenesis in Europe. Thank you for joining us today. Today's presentation is called The Multiplication Effect, How Synergistic Remediation Can Achieve Stringent Targets for Chlorinated Solvent Treatment. It will be given by my colleagues Todd Harrington, who is the Director of Product Management based in the US, and Marcello Carboni, our Europe Regional Manager, who is based in Italy. Before we start, I want to cover a couple of admin things. If you have any trouble with sound or seeing the webinar as we go through here, the best thing to do is log out, switch off, switch on again, and come back in again. If you're still struggling, don't worry, this is being recorded. A couple of hours after the webinar is given, you'll be sent a link so that you can watch it at that time. I'd encourage you to ask questions throughout. There is a panel, should be on the right-hand side of your screen. You can just write your questions in there and we'll get to as many of those as we can at the end. If we run out of time, we're trying to keep this to about an hour. What we'll do is email you the questions afterwards. And if you think of questions over the next couple of days, do email them in and Todd and Marcello will get back to you. So that's everything we've got. I'll now hand over to Marcello to start the presentation. Thank you very much.
Thank you, Gareth, and hello, everybody. What will be the agenda today? We will be focusing on challenging on remediating chlorinated solvents, especially on a specific scenario. This is when we need to treat them at the property boundaries, removing off-site liability, protecting external sensitive receptors. We will see how this traditionally is being managed and an innovative solution. This is with injectable permeable reactive barriers. We will see the concept. We will see the technologies that will be involved in it one by one, in situ, sorption, ISCER, ERD. But then really what is the focus of this presentation is understanding the synergistic effect of combining all of them together. Then I will pass on to Todd. He will exemplify this on modeling and also providing some tips on how to design these injectable barriers. We will have then 2 case studies and we will finish off, as Gareth was saying, with a Q&A session. So let's start it. Chlorinated solvents, what are they? They are usually extremely toxic contaminants, even at low concentration. One peculiar thing, and this is, I'm thinking especially on chlorinated ethenes, PCE and TCE, when they break down, they form even more toxic compounds, such as vinyl chloride. They also tend to form pretty long plume. This is because when they are in groundwater, they tend to be relatively mobile. What does this bring to challenges in remediation then is that in many legislations, we are forced to go to very stringent target levels, especially when we are aggressing site boundaries. And this target level can be even lower, the lowest level, when we are talking about the daughter products such as vinyl chloride again. If then we are focusing specifically on the property boundaries, if we are at an operational site, we might lack of good space for provide this treatment, and we might need in many cases to treat this ongoing plume for a long time, years or even decades. In which scenarios? When I cannot do a source treatment, or where there is long distance between my source treatment and my boundary treatment. So I need to allow for time for this plume to attenuate over the years. So this all brings challenging needings in the remediation when I need to treat chlorinated solvents in my boundary treatment, because I need to go very low. I need to maintain this stably over a long-term period. So how has this been traditionally being managed? I have multiple options for this containment. This can be hydraulic containment, pump and treat, physical containment such as slurry walls, sheet piles, or another concept is permeable reactive barrier. Different approaches, but together they tend to be, all of them, quite impactful on my site setting, and also tend to bring up cost for the treatment, especially if I'm considering their use on a high number of years. And think about, for example, hydraulic containment pump and treat. If I need to install at my property boundary a pump and treat plant, and I need to run it over years, easily I build up cost on my treatment. If I then try to switch from a containment approach to a remediation use of this technology, then I get with the well-known issues of getting asymptotic effect and rebound when I try to switch them off. Physical containment, these slurry walls, sheet piles, they tend to be used typically when it's high concentration involved on the site. So try to confine physically my contaminated part area of the site. They tend to build up cost quite easily, even for small size. And this is why basically their use is not as well spread out as the pump and treat, which tends to be much more common solution. Also, I'm creating physical walls, so I'm forced then to manage over the time, basically forever, hydraulically my groundwater. Otherwise, I risk to have some portion of my site which suffer from flooding. And then from the concept of an impermeable barrier, an advancement has been the permeable reactive barrier concept. So again, a wall, but this wall is permeable to water, but while the groundwater is passing through, then the contaminants are getting treated. This is achieved by excavating natural soil and replacing it with some reactive material plus filling material. The concept is very clever, but due to the fact that I need to excavate and replace, then I'm technically limited on the depth that I can reach, and also again here, high impact and high cost building up. And this is why really we see a lower number of cases globally of this solution. But the idea is very smart, so smart that then it has been developed into injectable permeable reactive barrier. So the same concept, but instead of excavating the soil and replacing with material, I simply inject the reagents from the surface. And what I need to achieve is that in the subsurface, the radius of influence would overlap in order to create a barrier which can be considered continuous. And just doing that, then I increase in cost efficiency because I'm in a completely passive system. It's more getting less interference with site ongoing activities, and generally tends to be more sustainable. And basically, these benefits make that nowadays it is very well accepted in the majority of regulatory environments. Okay, the idea is good, but until arriving to a level of development that would allow me to go with extremely good efficiency, then it took really a while, because basically we are asking to these in situ technologies to provide me consistency and reliability on getting very down in concentration, maintain them stably, doing this job very quickly, and then maintaining on the long term. So it's characteristic which is not very easy to reach generally. So it took literally many years of research and development advancement until arriving to the level of being able to provide this consistently. Because basically, in order to be effective, these injectable substrates need to distribute well. And I mean, not just widely, but also homogeneously. They need to be reactive. And I mean, also the kinetics need to be pretty high. They need to last for long term, especially if I'm considering that there is a continuous ongoing influx of contamination arriving to my barrier at the boundary. And basically, this is being achieved with reagents that in general are colloids. So basically, we are taking advantages from solid reagents, which in general terms, they tend to bring good kinetics, good reactivity, but also persistence, longevity. We are bringing them into a fluid colloidal form, which provides to us very good distribution. And these become ideal media for creating these injectable reactive barriers. So let's see now one by one these technologies, these approaches. We will go through sorption, reduction, and biological degradation. Starting from the sorption, basically this is the concept of applying a sorbing medium inside the aquifer. This would provide an engineering of our natural fraction of organic carbon. So basically, it's a way of strongly retarding our contaminants. So the contaminants are slowed down in their transportation capability, and these immediately increase dramatically the retention time we have for the treatment in our barrier. Another advantage is that the contaminants are quickly removed from the dissolve phase, from where they provide direct risk pathways. Activity carbon is well known for being a very effective sorbing media, but then if we are considering granular activity carbon, its size is good just for external ex situ filters. If we're going down to powder activity carbon, this is usually used for air stripping treatment system. In order to inject, we would need high pressure, and this provides fracturing, which is not providing any homogeneous distribution, which instead can be only achieved by colloidal activity carbon. Colloidal activity carbon has got the size of 1 or 2 micron. We are able to suspend it into we are able to suspend it into a liquid, into water, basically making it become a black liquid, a black ink, which can be dispersed over time. Sorry, be dispersed over time and providing very homogeneous distribution inside our aquifer. It is not just a matter of improved distribution on the colloidal activity carbon. This provides also increased kinetics. It is already understood that powder activity carbon is quicker and more effective than granular activity carbon. This is because of easier accessibility of the sorption site on the activity carbon. In the same way, colloidal activity carbon has got a better kinetics compared to both powder and granular. And let's get into The second treatment, this is enhanced reductive dechlorination. Enhanced reductive dechlorination is a biological mediated reaction. So there are microbes which are using the available hydrogen, and this available dissolved hydrogen is then being substituted to the chlorine in the chlorinated molecule. So this provides that I get a sequential transformation until arriving to 18. And this is a typical characteristic of anaerobic biodegradation. So I'm forced to temporarily pass through DCE, and I get some temporary buildup of the vinyl chloride. What is the advancement here? So we are getting a colloidal solid electron donor, such as the Aquifix. This has got a very good distribution, but on top of this, being solid, this can get to extreme longevity. We're talking about more than 10 years of longevity. And this extreme longevity is important, especially if we are considering this scenario we're talking today about creating barriers at boundaries. On top of this, it's also completely compatible with the other colloidal reagents that are usually combined together. And let's get into the last one. This is in situ chemical reduction. This is provided by zero valent iron, so a chemical reducing reaction, which is able to form an abiotic pathway. This is what we are seeing down, and this is the beta elimination process. We are seeing from these that the very interesting part is that we are able to maximize this pathway, minimizing then the formation of DCE and vinyl chloride. And this is a very interesting thing if we compare to the enhanced reductive dechlorination. Another interesting benefit is the fact that being chemical reaction, this tends to be faster compared to the biological pathway. And what are the advancement here are getting not only a colloidal zero valent iron, so not a solid particle, but something which is fluid, therefore can distribute again very well. On top of this is also sulfidated. It means we have an iron sulfide layer which maximizes the reactivity, direct reactivity with the chlorinated solvents. So many times more reactive compared to bare iron. On top of this, we have avoidance and minimization of passivation, so the iron doesn't rust, and we get a product with increased longevity. We're talking about more than 4 years. Again, so a very interesting concept if we are building up injectable barriers. So we have seen 3 different technologies, 3 different products that already self-standing have got very interesting advantages. So the plume stop can provide being carbon rapid reduction in concentration and can maintain them to low concentration very, very stable. But if I'm considering this technology alone, then in itself, the activated carbon does not bring any destruction pathway. So I risk about getting to breakthrough over time in my barrier. The S micro ZVI being iron, it can provide rapid chemical destruction, minimizing the formation of the daughter products. And I can target very high concentration. But again, if I'm considering this alone, then ISCR tends to be with slower kinetics with the DC and the vinyl chloride. And also I would be forced to use a very tight spacing in my injection line. Aquifix, enhanced reductive dechlorination, instead is able to provide very effective biological degradation also of the daughter products, unlike the ISCR. and is able to provide very wide distribution on the very long term and providing me very low target. But again, if I consider it alone, then ERD tends to be slow. So I may also risk that it can be difficult to build up a barrier with a good enough retention time in order to provide the process entirely in my few meters of barrier. So the answer in order to maximize the efficiency of this treatment is getting them together. So basically getting a synergistic approach. And it might seem that we have gone a little bit too high for calling Aristotle for explaining this concept. So the wall, basically, the effect of combination is greater than just the single sum of its part. And here maybe we have gone instead a little bit too low for explaining this concept, especially if we think that we are on Wednesday lunchtime, pretty far away from the weekend. But basically, this is really what we are talking about. So taking three different liquids, which already are very good as standalone, but it's really when we mix together that we are getting something which is superior. And really, the mixing part is not a thing. So this is very straightforward. Just we are getting our mixing tank with water. We are including our plume stop colloidal activity carbon in it. We mix. We add the Aquifix colloidal electron donor and continue the mixing. We add the S-microZVI sulfidated colloidal zero valent iron. And we obtain very quickly a single low viscosity injectable substrate that we can apply at low pressure injection. At that point, you might ask, okay, but why Regenesis does not invent just a single reagent which already contains all the three of them together? The answer is basically maintaining them separately, we can allow for flexibility. We can dose based on the site-specific needs, and this increases the technical and the cost efficiency of the treatment. But let's go and see more into details what's happening down in the groundwater when we are applying such a combined system. So basically, I'm getting the activated carbon into the aquifer. This very quickly takes out the dissolved contaminants out of the solution, and they are getting into the activated carbon surface. Then, thanks to the fact that I've got iron, I rapidly establish reducing conditions, so low redox potential in my aquifer, and the electron donor instead is supporting the growth of my dechlorinating bacteria. Then the fact that the activated carbon is staying on the solid soil surface, so it's basically coating my aquifer matrix. This is also where my zero valent iron will go. And so this proximity in the same region of the aquifer makes that there is enhanced contact between the sorbed contaminant and the zero valent iron. So this makes that also the fact that the contaminants are sorbed onto the carbon, also my microbes tend to be benthic sessile. So it means that they are growing on solid surface. So also the microbes will grow on the same region of the aquifers where the activated carbon and the zero valent iron. This makes that I can get very quick chemical destruction of the parent compound, especially because ISCER is especially effective with parent compounds, minimizing the formation of the daughter products. This is because I go basically by beta elimination pathway predominantly. But if I get accidentally any daughter products produce, then I get the enhanced reductive dechlorination, which is very effective into biologically degrading them. And also what carbon is providing is that it increases dramatically the retention time within my treatment barrier. So basically it slows down the contaminants in my treatment area. Therefore, the contaminants will stay a longer time inside my treatment barrier portion of the site. And so I can extend this contact and I can get powerful mass reduction, even if I'm starting from high concentration. And this longer time also achieves to get biodegradation, the time to arrive to very low concentrations. What are the ISCR and the ERD providing then, if you look, is complete regeneration of my sorption site on the activated carbon. So basically, the activated carbon does not consume over the process. It will be with sorption site freed up to sorb additional influx, which is coming from up gradient of my barrier. And then further sorption allow for more contact, more chemical destruction, and more biodegradation ongoing. And this is going over and over on the very long term, on the multiple years range, to provide a self-regeneration process where I get sorbed the contaminants and then the sorption site cleaned up by both the abiotic and biotic processes. Let's see this in practice, how it happens, and let's scale up on the aquifer. So what we're getting is injecting the colloidal activity particles of a plume stop after few weeks would be adhering to the solid soil matrix. This means creating a very thin film on top of a solid surface. And from this being carbon, it immediately sorbs the dissolved contaminant. The colloidal zero valent iron particle would settle down in the same area. So again, on the solid surface. So there is extreme proximity between the contaminants that are sorbed and the zero valent iron. And this provides very good exchange of electrons for direct chemical reduction. Also, the aquifix, the colloidal electron donor, would go in the same region. From there, slowly over multiple years' time, there will be dissolved simpler organic acids. These are the ones that then are releasing the hydrogen, which is feeding the bacteria in charge for metabolization of our chlorinated solvents, which again are sitting in the same surroundings as the activated carbon and the zero valent iron. So this process immediately removes the contamination, so taking out of the dissolved phase and also treating, but also then on the long term, whenever influx is continuing to arrive to my treatment area, is continuing to manage and to treat and to keep my barrier clean over the time again. Okay, I'll pass on to Todd, which will explain us this concept from a modeling point of view and which will provide information about the design. We will see each other again with a second case study. Okay, on to you, Todd.
All right, excellent. Let's see here. All right, so All right. Welcome, everybody. Marcello, thank you for that excellent overview. So I think what we can say is it's elegant and it's complex. The use of this colloidal chemistry can create quite exquisite, barriers and results. And I thought that transitioning from the overview of colloidal would help to, take a look at some of the tools that we use a model and how we visualize performance of a barrier, actually how we design barriers, and it'll help illustrate the synergistic effect of, say, iron with carbon, with an electron donor, etc. And how we design this in the office and then transitioning into the field. So how do we model, say, a permeable reactive barrier here at Regenesis for our clients? Well, it's something that we've been developing for a while. If anybody's watched our webinars in the past, you've probably run across and heard of Plume Force. It was developed by our own Dr. Jeremy Bernstengel out of the UK. He's our VP of Environmental Technology. This is a multi-phase finite difference model that factors in dynamic sorption, factors in this, contaminant destruction through the methods that Marcello just described, including competitive interactions between contaminants themselves and other species of organics that might be in the subsurface that might compete. And so in terms of the models go, we enter inputs such as mass flux, concentration, velocity, first order rates. Obviously dimensions, we're really focusing on the implementation of IPRBs in this webinar. So say the width, the vertical injection interval of a barrier, and time, how long does it need to last? And that allows us to explore scenarios. It allows us to adjust dose rates. And so I'm not going to get into more of the technical on what this model does. It's just outside the time we have today. But if you'd like to, take a screenshot or use your phone and visit a recent webinar series that we had or watch, please do so. The cross section, some of the data that I'm going to get in today is more related to webinar number 1, modeling and design. So just for reference, that would be a good one. So with that frame of reference, what we have is we're using Plume Force, and I'm going to show you, what would we see if we had a barrier of a certain width at a site where we were trying to stop migration. So what we have here is an actual output that we get from this model. The chart on the right is vertical axis is concentration, and the horizontal axis is distance in feet. Now, the default for this model was created in feet versus meters, so I apologize for that. But the seepage velocity that we're going to use as a standard here is 61 meters per year. And this is an example of nothing turned on in the model. There's no sorption, there's no reduction, there's no biodegradation. It's just moving from the left to the right, uninhibited. And we've got a hypothetical plume that has both PCE all the way down to the daughter product vinyl chloride. And vinyl chloride is shown in the red at the bottom line here, whereas PCE is shown in blue up on top. So let's imagine here, many of you probably have experience with enhanced reductive dechlorination. We've talked about that with our Aquafix product here. What happens if we just do an electron donor barrier at a site? Now, in the older days of Regenesis, we would use HRC, hydrogen release compound product. But one of the points we need to make is that challenges is we cannot put a hydrophobic product or various products of different viscosities with our plume stop, and that's one reason that we created Aquafix. But with respect to just putting in a donor, we imagine one that's about 3 meters thick here as designated by the span where I'm pointing in my cursor. And what it's showing is that we start to get rid of the PCE, we start to convert the PCE to trichloroethylene, and then that starts to increase from that conversion process. Now, TCE also dechlorinates and starts to form a DCE, but the half-lives are too slow to actually accomplish a full dechlorination to innocuous byproducts before it leaks out of the aquifer. As you can see, we have plenty of vinyl chloride, plenty of DC coming out of that. So this would not be considered an effective barrier, in a theoretically, perfect world here on that. But let's switch the thought apparent. What if we did Iskar only? What if we did the zero valent iron, as a form of S-micro-ZBI? That's interesting because we know that the kinetics for chemical reduction from this are pretty fast. So you can see here that the blue line and the orange lines are PCE and TCE, and those are destroyed pretty quickly, and you see the generation of the end product ethene right here. You can see that happening. In this particular case, though, the kinetics of that reaction are too slow to effectively handle the DCE or the vinyl chloride. S-micro, the kinetics on that are typically too slow for it to handle it on its own. So what we see is the influx is not as treated as effectively for the daughter products. In terms of absorption only, as we can imagine, if we just turn off bio and we turn off chemical reduction, we get what you can imagine. Now, because I'm doing time plots, and I guess I forgot to say this earlier, we're just, instead of doing a lot of simulations where I show you 1, 2, 3 years, I'm just showing you at, say, year 7, if we wanted to have at least a 7-year barrier, at steady state. And so if we have contaminants impacting a colloidal activated carbon barrier with no destruction, eventually it's going to fill up and pass through. And we're talking milligrams per liter or, high, ppb concentrations here. You can see the PCE is stopped. You can see that other things pass through. But let's get to where it's interesting, where things are added together. Now, this one is relevant because it's going to be related to a case study that I show here in the next few minutes. And what if we hold things in place with colloidal carbon and then cause some destruction by the S-micro-ZBI? And you can see that it actually works quite well. We're not actually getting any leakage at 7 years. We're holding on to that. Even though ZBI has relatively poor kinetics for vinyl chloride, we're holding it long enough that we're actually getting it to not come out of this 3-meter wide barrier. Now, it's a little too close for my comfort, and I know our designers, as our geologists, engineers, our designers, would probably approach this a little bit differently if we know that we have vinyl chloride coming in and DC coming in, continuous feed. We'd probably add a biological component on this particular one. But when we do add that component, what we see is we see a full effective reduction in dechlorination, top to bottom of the parent compounds and the daughter products. And if you're looking at how far vinyl chloride has made it through this barrier, it's only about halfway through at 7 years. So, assuming the longevity of 10 years for Aquafix, assuming, 4+ years or more for zero valent iron, we're seeing something very effective here, with this. And so this is, hopefully this shows in a real practical way how these products can combine for something really effective. All right, so let's just take that. We're going to shift directions right now. We're actually going to go to the final part of our presentation today, and we're going to get into 2 studies, case studies. I'm going to talk about the first one, and this first one is a site where we actually used multiple colloidal barriers to address an elongated TCE plume into protective river. Now, this site was located in the state of Indiana in the United States. For reference, it's roughly about a third of the way into the US, east to west and just south of the Great Lakes region. But this chemical manufacturing facility had released TCE in that process, and TCE only that was detected below a warehouse that resulted in a greater than 500-meter TCE plume migrating to a surface water body and moving through different zones of an aquifer that could get relatively thick. And I'll show you a cross section here in a couple minutes. Working with a client is a really good client to work with, but they wanted probably the same things that you might be sitting there thinking that you need if you have any sites in mind in terms of ideal solution. They wanted something flexible because this was a built out warehouse district. There wasn't a lot of room to really go in and put in treatments or barriers. Had to be flexible that way. Certainly had to stop migration into the river and definitely stop or not produce vinyl chloride. And certainly we wanted to be cost effective and fast. So same things that most everybody wants if we can have that. In terms of the approach, now I'm going to say that I'm going to be focusing on just one part of the approach, but there was two approaches. The first we're calling the source area remediation. If you look up here to the upper right, there's two red barriers. Now, the reason I'm not going to focus on this today is that the client chose to use thermal in situ thermal remediation. So, heating up the soil and groundwater to extremely high temperatures to desiccate the soils, to start extracting the vapors, and really actually using that heat to promote biodegradation. So they actually put in 3D microemulsion, which is one of our electronic donors that's actually not compatible with colloidal activated carbon together, some bacteria, some other products, really with the goal of supercharging biodegradation in conjunction with the thermo. So there was no colloidal activated carbon put up there. However, coming out of the source area here, we're going to be looking at these pink barriers where we needed to effectively prevent the ongoing movement of contamination, and that is where we decided to use a combination of colloidal activated carbon as plume stop and our S-micro ZBI. So the challenge is that looking at a cross section here, the cross section shows left to right source area to toe of plume. The thickness of the aquifer, which is in green, which was the permeable part of the aquifer, was confined at depth by a clay zone, was shown in the hatched gray part down here. The thickness ranged from just under 3 meters to just over 6 meters thick, which is getting relatively thick, and we recognize we're going to need a little bit of optimization out here. Do we need to go as wide? Do we need to go as deep as we think we might have to do? So if, typical with what we do at Regenesis, and certainly another topic that we can go pretty deep into, we typically like to go out and do some additional work ahead of actual full scale. It's not necessarily a pilot test, but it's reevaluating and locking in the variables for a site. Now, we call it a design verification testing phase. It's where we would use something like a flux tracer, and I'm going to mention that. Regenesis has a unit you can put in a well to very accurately measure mass flux. We've really migrated to using these within Regenesis a lot. So we take this field data, go back to the office, tweak our designs, then move to full scale. The full scale can have a component where we inject and possibly use the product as a tracer, slow the rigs down, stop, take some observations. Are we getting distribution? Yes, no. And then move forward and review the technical performance. So it's a really good feedback loop to make sure that we've got a good design and good application in the field. So we did indeed do that on this site. We went out before the initial application. We did some test injections. We optimized the tooling we were using, the pressure, the volumes. We actually employed a very important unit, which I'm going to focus on here in the next couple slides, called a passive flux meter. Now, Regenesis has one called a flux tracer, which I just mentioned. There's a great company in Europe too. There's one called iFlux. So we've had some great success with them. Either unit can get the results that we need. And why am I talking about this? Well, again, I'm throwing out a fairly important topic, but when we're doing a barrier, the one thing that we need to be concerned about is how much, say, TCE is passing the plane of a barrier over a period of time. And so typically as engineers and geologists, we'll think in terms of Darcy flux and seepage velocity. But what we like to think about more so at Regenesis is mass flux. And the concept with that is that aquifers, you know, as they experience contamination over time, and as they have heterogeneity, or say different conductive zones sandwiched between clay zones or on top of clay zones, you can have water moving through at much different velocities. And then when you add the fact that you can have different concentrations, you can have the movement of flux or contaminant flux across the plane of say a barrier at rates in which a monitoring well might not detect. When we take slug drawdown tests or slug tests from a monitoring well, we're typically getting an average, but what we're finding, and one thing that we've really had to grapple with at Regenesis, is the fact that there can be zones within an aquifer that are as little as 1/3 of a meter that are carrying up to 80% of the flux of a plume. And if we take an average, we risk underperformance or breakthrough of that barrier sooner than we anticipate. So how do we measure max flux? I mean, obviously I made the case that we're trying to avoid some traditional methods. I would say state of the art is generally avoiding use of pump tests or slug tests, avoiding averaging techniques, and leaning towards high resolution techniques using these flux tracers. Now they could cost a few thousand euro, say per well to put them in there. You put them in for 2 weeks, takes a few weeks to get the results back. But what you get is you actually get flux by vertical interval at resolutions under, even tighter than 1/3 of a meter within a well. And when you get that information, you're going to identify those zones that are moving at high rates, and you can plug the gap. So if you want to know any more about that, I'm going to actually get into just more of the results of the study. But we did perform flux tracers out there, and feel free to take a screenshot or a snapshot of this QR code to a webinar that we did a couple years that goes into some excellent detail on this technology. So the results that we get from that is, this is an actual flux tracer result on the lower right. This chart here is showing the depth below the top of the well casing, and horizontally is showing mass flux in terms of milligrams per meter squared per day. What's interesting is when we took a soil core, we found that this conductive zone, which visibly looks conductive, you can see all the sand there, was actually taking a majority of the contamination. This area here was just about a meter thick, which was taking a majority, as I said, about 80% of the flux of this aquifer. We're able to take this information from these flux units and go back and redesign our original dose rates to focus a majority of the material at that location. And there was actually some good news. So even though the flux tracers add, in this case, they added about $18,000 US to this project, what we found is that in this situation, we had vastly actually overestimated the seepage velocities at the site. Our original design assumed we were going at about 400 meters per year. It turns out that the flux tracer analysis that we did said it was closer to 100 meters a year. So it was moving a lot more slow. We were able to reduce the amount of product we needed significantly. And we also found out that on wings or parts of the width of the barrier where we thought we were going to need to inject material, there was absolutely zero mass flux. We weren't picking up any TCE on this plume. And so that information alone, according to the client in our design, we saved them about $380,000 US in injected material on that. And that doesn't even include injection. So this is easily over $500,000 in savings on this project, particularly just for using about 17,000 in passive flux meters. So really good on that. Now we did ensure that we were injecting the material correctly. And you can see here the conductive zones of the aquifer. This is after we did an injection, that we're getting a nice uniform distribution of both the plume stop material and S-micro ZVI. And we injected for about 56 days from October 2022 to January 2023, about 420,000 liters of amendment, injecting from roughly 5.4 to 10.5, depending on the barrier location, meters below ground surface. out there, and you know, we're looking at about just under 30,000 kilograms of plume stop and under roughly 9,000 kilograms or so of S micro ZVI. In terms of results, 3 months now, it took a few months before we could get in there and start sampling, and the sampling results, we did not get those until roughly summer of last year. But what we do see is we did see an 80% to 100% reduction in all locations. Now this is pre-injection, and then you can see first application, first post-application monitoring event, third quarter of 2023, showing just excellent results and just slicing the plume apart and actually preventing the continued migration of TCE, you know, towards this river. Going to the next quarter, just looking into the fourth quarter of last year, we can see the results holding steady. First quarter of this year, we can see the results holding steady there as well. We're going to continue to monitor that, but as a montage, you can see how we've been able to significantly, you know, treat this plume over time. We're going to obviously, like I said, continue to monitor. The client is extremely happy with that. But hopefully that's a really good example when, you know, good design, a good field feedback, you know, some of the results that we can get with these colloidal technologies. So with that, Marcello, I do want to hand it back to you.
Okay, thank you, Todd. And let's get into the second case study. And this time we are going back to Europe and specifically in Italy. I will go a little bit quicker because I'm seeing that we are running out of time. So here the situation is a former manufacturing facility, a redevelopment company which was willing to build up 3 residential buildings in this site. From a geologic point of view, we are in sand and gravel units in a fast flowing aquifer. So this is going towards challenging conditions for this quick aquifer to install injectable barriers. From a contamination point of view, at the boundaries, we were not having very high concentrations, so some tens of micrograms per liter PCNTC, some already daughter products formed by natural attenuation. The point is that the legislation was forcing to get into very stringent table limits at the property boundaries. So 1.1 micrograms per liter PCE, 1.5 TCE, and 0.5 vinyl chloride, which is the most challenging to reach, obviously. So the goal for the client was to obtain something very quickly. So hopefully before that they would be able to sell the properties, so selling the properties without any pending environmental liability to the new owners, minimizing interference with ongoing construction activities, and getting something very stable to low concentration on the long term, because there was a long-term monitoring. So the typical environmental requirements that are requested in this condition, as we have seen previously in the previous part of the presentation. So the solution was an injectable PRB, going with all the 3 single technologies combined together, so sorption, ISCR, and DRD. So basically providing those benefits that we discussed earlier. So this translated into a full-scale application, a barrier which is 25 meters wide and 8 meters deep, where we mixed the different reagents together. So if you look, like we didn't use the Aquifix because that site application was prior to the Aquifix launch. So we had been using another different electron donor. Having the Aquifix would have brought also the advantage, for example, of being able to mix all the three together in the same mix. Also, in this case, we did a lot of design verification testing prior the injection and during the injection. I wouldn't touch on it, but I would jump directly onto the results we obtain. So first, let's see the parent compounds. Those are being knocked down very, very quickly. So at the first monitoring point, 1 month after the injection, already below those stringent targets. This is also because parent compounds are being very effectively treated both by sorption, so they are not very mobile, they're very sorptive contaminants, and by ISCR. We say zero valent iron is more effective with a quicker kinetics on PCE and TCE. What are we getting then with the daughter compounds? Also them are rather quick, and I mean in few months being also them below the stringent target. So we just needed some months to get vinylchloride below that 0.5 target level, and then maintaining this over time over the different monitoring campaigns performed. And what is very interesting is that we are observing that probably we are not creating any daughter products through the treatment. So it's simply what we're doing is managing daughter products already formed previous prior the application formed by natural attenuation. So concluding on this case study, basically we have seen how this combination has been very efficient in optimizing to get very low stable target concentration and maintaining it on the long term, minimizing the daughter product. And so on a single injection, minimizing interference without any installation of a fixed treatment plant on site, the client was able to get to closure and to sell their residential properties. So recapping into lesson learned of this presentation. So we have seen how advancement in research and development has finally been able to get into the level of having single remediation technologies, which as standalone already are very effective. So in situ sorption, ERD and ISCR brought at a very high effective level. But it's really the synergistic effect of the combination of all the three together, which is bringing this to a superior level, where we are able now finally also to target very challenging sites with site-specific conditions, which are not very easy to treat. And this is also minimizing the equipment that is needed on site, providing a passive treatment without energy consumption. So basically, generally speaking, being able to provide these at affordable cost with very low carbon footprint. So generally, high sustainability solutions without providing waste production. Okay, with that, I've concluded, so I'll pass on to Gareth to see if there are any questions.
Thanks, Marcello, and thanks, Todd. That was really great. We do have a lot of questions. I'm going to ask a few of them to you both now. Anyone who hasn't asked a question and who has a burning question, please just enter them now. And again, if you think of something later on, please just email and the guys will get back to you. So first question, does the activated carbon eventually wash off the soils? Anyone want to take that?
I can take that. So the short answer is no. So basically, let's say this way, we made a lot of effort to make the carbon being stable in water, because naturally activated carbon, being carbon, is organic, so it's in itself, it's highly, strongly hydrophobic, so it's really attracted by the soil matrix. So we temporarily succeed into getting this into water, but this is functional just for the manufacturing, for bringing the product on site. Once it is injected, this stability in suspension really lasts quite short. So it's just functional to the distribution of the product. Once it is settling down, this attachment to the soil is permanent. So we do not risk about washing out.
Okay, thank you. Next one, are there limits to treatment such as contaminant concentrations or groundwater flow rate?
It's a good question. Marcello, I can answer that.
Okay.
Yeah, I guess related to, like, as we look at the modeling, so certainly there can be limitations, but it depends. So certainly the remedial goals, you can have groundwater velocity that is, so fast, and let's say you're dealing with vinyl chloride, where, it could be problematic. But I would say that we can typically provide solutions for a wide variety of sites, effectively. So like I said, it depends. And I said most situations that we run into, we were able to come up with an effective combination on that. There are variables that will come up that we have to look for. Certainly acidic aquifers, if you've got low pH, that can be problematic for the iron. It could reduce its lifespan. So we're talking low, like 5.43 for pH, something like that. We would look out for things like that. Things that are obvious, maybe depth, might be a bit of a challenge. If you're getting more than, 15, 20 meters below ground surface, we might have to look at some wells. You don't know, but there's other logistical things there. But in terms of actually the level of concentration, it's really going to depend on flux and the gold we need. And a lot of times we can put multiple barriers in if needed. A lot of times we can do just fine with a single barrier, but we have that flexibility.
Thanks, Todd. The next question's linked, actually, so maybe you keep going on that one. It's does the geology have an effect on the dose or the injections?
You bet. Yeah, it certainly does. It does in a couple ways, because, say, a tighter geology, one with more silt and clay, certainly there's going to be more storage units. We'd probably be more concerned with long-term, like a phenomenon called back diffusion, which we also think about a lot. But the one thing that people probably think about is tight soils like clay, is like, can you even get this product, in the ground? One of the things we think about with colloidal technology is we think a lot about we call them flux zones. It's where's the contamination moving? These zones can be found by the passive flux meters that I mentioned. And so really, if groundwater is moving, if there's a plume moving, it's probably moving through a sandy or a silty, but not all clay zone. And as long as we can find those, we can target those. So in that respect, yes, we can handle the tighter sites.
Okay. Couple more. Are breakdown products such as vinyl chloride sorbed by the barrier?
I can take on these. Yes, to a certain degree. Of course, I mean, not all contaminants are sorbed the same. So basically, on these, colloidal activated carbon works as any activated carbon we are considering in a filter. So basically, we have sorption isotherm on the plume stop for each single contaminant, and the sorption isotherm of the vinyl chloride, being more mobile, is less favorable to sorption compared, for example, to the PCE or TCE. But say that we are able to provide sorption also of vinaigrette. Of course, being, let's say, in the same site, same concentration, we would need more carbon to get the same effect of sorption compared to the same concentration of PCE or TCE. But then basically, the model that Todd did show you helps us also in seeing and evaluating the effect. And it's really not just the sorption capability that we are considering, it's also how much they get distracted by the chemical reduction and the biological removal, basically.
Okay. Thank you. And there's somebody asking about the cost of the barriers that were mentioned today. Can we share anything on that?
So I can speak about mine. So the second case study, if I'm not wrong, the cumulative cost of all the activities was around 200,000 euros. And I didn't mention this during the presentation. This was also including a sort of guarantee for the client for success. This is something we do not always provide. We just can provide sometimes based on the request of the client. So this was meaning that in this amount of money was included also any extra contingency activity which could have been needed in order to arrive to the target levels.
Okay.
Yeah. For the one that I showed in the US, I think that was around, certainly we saved 380,000. It was a large system of barriers. I think the product cost, I guess, probably close to just over 600,000 euro. I'm not sure of the delivery cost exactly, but I think it was probably at least 50% on top of that. So under $1 million for that, for sure, but quite a large area that we were treating.
Mm-hmm, for sure. Okay, we're running out of time, so I'll just ask one more question. And as I keep saying, keep sending in questions. We will get back to you. But the one more question then. So can these barriers treat non-chlorinated contaminants, and what about NAPL?
Okay, shall I get this?
I can jump in on that.
Okay.
Yeah, so I guess, yes, we can treat other contaminants. So the idea is that certainly, you know, anything that will adsorb to an activated carbon. So we do treat hydrocarbons. We actually have a different product line for that called Petrofix, but certainly other types of solvents, organics that we might run into, we can do that as well. So no, it's not just limited to trichloroethylene or the solvents on that. In terms of L-NAPL, I guess that specific focus, you know, we like to say that this is a groundwater treatment technology, like particularly for the barrier. We're not putting these in to DNAPL or L-NAPL. There's just really not enough activated carbon for this application. You know, we're putting in an effective barrier for groundwater treatment, not the loading rates from a direct, you know, mass flux from an L-NAPL or DNAPL source on that. So no, not designed to treat that.
Okay, perfect. I think we'll stop there because we keep going. Oh, sorry, go on, Marcello.
No, I just wanted to add, in case, I mean, there are cases where there is a plume aggressing the property boundaries, which also includes some NAPL. Let's say it can be more often, let's say for hydrocarbons. In this case, like an idea could be to remove the NAPL prior to the getting onto an in situ barriers, such like this. So basically getting into our in situ solution after having done a more up gradient, a removal of this NAPL, for example.
Yeah, that was a good point. Good point. Okay, perfect. We'll stop that there. Thank you, everyone. In the next hour, you're going to receive an email from us with your attendance certificate. There's a link in there to a short survey. It'd be great if you could just take a moment to fill that in for us. On there as well, we're asking for other topics, other presenters. anything you'd like us to talk about. We are planning in our talks going through into 2025 now. So tell me what your burning interest is, and we'll try to meet that. But thank you for joining us today. Thanks, Marcello. Thanks, Todd. I hope everyone has a good rest of the day. Thanks, Sam. Bye.
Thank you very much. Bye.